And we're going to start now. Let's do this. Hello, everyone. Welcome to my video about methyl orange, and we're going to look at the mechanism in this video as opposed to the actual lab. For more information on the lab with some tips and theory explained, see my next video. So, jumping right into it, the plausible mechanism for methyl orange is quite lengthy and quite complex. As you can see here, it is a lot of arrows. So, the big thing here is we've got um, three origins of this mechanism that you can imagine as three flasks that eventually mix together and form our main product here at the bottom. And we have to understand that this mechanism comes from three directions. All right. So the first direction is coming from here. The second direction coming from here. And the last one here. Those are your 3 points, right? So I will just delete that again for you. And now we're going to zoom in a little bit so that you can have a better view. I would suggest you save this, you take a screenshot and you save it. Because what we're going to do in this whole video, we're going to zoom in very much on just like one interaction or two interactions. And then you might get confused from where exactly on the bigger picture we are with the reaction. So I would advise you to come back to this overall reaction every time you feel lost to see where are we in the reaction. So like I've mentioned before, this is our first starting point right here. Let me just click there. Yep. This is our first starting point right here. And the reaction goes like this. And here it stops. This is our first reaction done. Then it continues on the other end. It continues here and it goes like this, where it joins with the second origin coming in here. Then it makes this little swirl here. And you see if we go down, 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 and we go to our final product, this is the last number 3 origin. And that's our product. Well, our neutral product, this is our acidic product. We're going to have 2 products. So let me just clean this up for you. I want you to be able to see the molecules when I discuss them. So I will do you a favor and I'm going to zoom in even more. And you can pause this video and you can take note of what is here. Oh, let me just remove that as well. There we go. So yeah, you can refer back to this in the end. I'm just going to very slowly move so that you can see all the molecules that and the interactions that goes within this reaction for yourself. All right. Well, now that we have the full mechanism, let's go in it bit by bit. This is our first entry right here. Let's move this a little bit to the left. Let's zoom in a little bit more. There we go. So here we have our first entry. This is the first step in the actual physical lab as well. You start by combining sodium carbonate and you start by adding sulfonilic acid and you add some heat to this. When you add heat to these two molecules, you're going to see an interaction where they would just exchange some protons, some um, atoms, some, let me explain to you this way. Look at the sulfonilic acid here. This is a molecule that's got both a basic amine and it's got an acidic sulfonyl at the top with that oxygen there, which is an alcohol. So this is not very acidic because this is a very nonpolar group here. And there's already so much bonds going on there. Here, on the other hand, amine already got two protons, doesn't really need a third one. Is it really all that basic? No. But with heat and the addition of CO3, um, and sodium on that, with other words, sodium carbonate, you will see the molecule reacting in the way that this amine here is going to form ammonia, which is NH3, by taking a hydride shift that's kind of like a long distance hydride shift, but it steals the proton at the alcohol at the top. And then we are sitting with this very nucleophilic basic oxide molecule that is going to steal their sodium away there from another oxygen, which is going to like the extra hydrogen that was just passed over to the ammonia molecule, right? So this is how our intermediate product looks at this point. It's now an acid, and it is now got this stability here with an oxide and a sodium on the other hand. Now, we did this without the addition of an acid. We are now going to add water and an acid together in this mixture. So this is going to change the dynamics completely. I want to say before we go to the next slide, when we add an acid here, it's important to add water with it because there's going to be a lot of hydrogen, proton donations, and so on. That needs to be effectively carried out by a hydronium ion that needs to be extremely acidic. So the reaction continues here where the arrow goes. And then when we go to the next slide, you'll see this is where we are going to now. Okay, so we ended here. Now we're going in here. This was the molecule on the previous slide. This has got nothing to do with us yet. We just ignore that for now, okay? So the reason why the molecules exchanged in the first place, where it wasn't all that basic, all that acidic, and yet it stole the sodium from one oxygen to the next, is because if you add an acid, it's going to form water and it's going to form carbon dioxide as the products. And that's a very thermodynamically favored product. It doesn't really need all that much activation energy, and it shifts this whole thing, this whole reaction forward. This was a very easy lab. I'm going to be dead honest with you. Like the physical work was not that hard. And you're probably going to get a good yield. You're going to get a molecule with very nice color. This is really a foolproof lab. It is because of the fact that the byproducts that form here are extremely stable and thermodynamically favored. And you start off with very unreactive regions, really, which takes us to the second start here. Now, it's important to note that we have added water and hydrochloric acid, but we also added it here, all right? So actually what effectively happened here is we applied it here on both sides, okay? So I hope that helps you. Put it there. So yeah, this is where we added that, and we added it with this specific region too, which is our sodium nitrate, okay? And a nitrate molecule is extremely unreactive. It's a very stable molecule. It really is not going to do much. And when you got the sodium there, yeah, you got some ionic interaction between the oxygen and the nitrogen and the sodium, and it is kind of stable, but we are using a very strong acid, which is hydrochloric acid, and we're using its um, 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 hydronium ion that is so acidic that it would get this stable oxide here to protonate itself. And also here, look at this. We got an acid here, right? That's a carbonyl, and that is an alcohol. That makes an acid. This acid is attacking another acid that is so much more acidic than that, so that it can form the water and the CO2. So where do we get acids attacking acids. Well, that is when your hydronium ion. Let me put it this way. Hydronium ion is something that you cannot buy online or at any chemist. You cannot isolate it. It's just theoretical, but it's a very real theory. It does function this way. It's just that you're not going to really see it in person. But the thing with hydronium ion and its theory is the stronger the acid, the stronger the hydronium ion is going to be. Hydronium ions doesn't always have the same strength in one reaction as opposed to the other. This acidity is directly correlating to how acidic the actual acid is that you have diluted with water. All right. Now let's talk about acids that you can use in this reaction. You need an acid that's going to damn, I'm so sorry, I forgot my words now. You're going to need an acid that's going to dissociate in water, okay? And it needs to form a very small and simple anion, and it needs to be giving its proton for water to make a hydronium ion. So in essence, you can use iodine, you can use bromine, but you cannot use sulfuric acid. It's too big, it's too bulky. You need a molecule that's going to be a single atom that's an anion, like just that, because the chlorine is going to play a very essential role in the stabilization of the intermediates and our final product. If the chlorine is not there, we're not going to get a final product, actually. And it needs to be something that's very keen and easy to keep close by bulky regions. So therefore, it needs to be small. Okay, so we're really looking just at hydrochloric acid, and HBr and IR and HI. And that's really what we are looking at. So in our case, we use hydrochloric acid. That's a great one to use. So this very unreactive nitro, it forms water, it synthesizes water, and with the electron density shifting down, it forms a triple bonded, resonance stable intermediate that's ready to go over into diazonium ion once it gets attacked by the very mildly mediocre nucleophile, which is this amine here at the bottom. So why does the amine attack this? Well, we know that two nitrogens do like to form a diazonium group. That's where you got one nitrogen and another one, and they're typically connected with a pi bond, right? And that is a favorite product. That's a formation in which nitrogen is very low in activation energy. It sets forth a bunch of subsequent reactions. It's just, you're going to see this a lot in chemistry, and that is the nitrogen double bond nitrogen. But that's not the case now. For now, we have a water-soluble sulfonilic acid, which it rearranged itself into this from our previous slide. And we sit with a triple bond here. Now, you would typically think that the the resonance needs to be for the nitrogen to be the cation, and then this nitrogen will pushes its electron density in an attack to that nitrogen to get the disonium, but that's not the case. The resonance structure that really does set this motion in play is when this triple bond causes the cation to be the oxygen. That's where the electron density is poor. And when this electron density starts to shift back up to the oxygen, when it is thirsty for those electrons, that's when the electrons start shifting out of this ring over the nitrogen. It just pushes over there. That's when it's going to join that motion, that pull, and it's going to connect itself to the nitrogen, what you wanted. Okay, so it's important to understand which resonance structure it attacks on, and that's why I've only given you one structure here. But in fact, you can really have the nitrogen at some point being the cation and the oxygen, the neutral molecule. Just take note. Again, what I should have put here is there is a chlorine also in this group here. So you have a complex here of oxygen, anion, a chlorine anion, and a sodium cation. They're just making this whole group here very stable. So it doesn't interfere with the rest of our reaction. And so the reaction continues now with this arrow goes, and this goes in here. This is where we were just at. As you can remember, we had the rearranged sulfonilic acid. And here we also have the oxygen that was bonded with a triple bond just a while ago with this nitrogen here. It's now connected here. So finally, we got our diazonium ion, but now there's not really enough electron density there to make a double bond, a pi bond, first of all. So we need that to take place. And also, our molecule in the end, we're hoping to attach another phenyl group with a para dimethyl amine, which is basically a dimethyl aniline, um, to this nitrogen. But here we got the oxygen in the way, and not just in the way, it's got two bonds. It's a pi bond that you need to get rid of and an oxygen. And now look at how very effective this nitronium ion is going to be, and look at how effective the chlorine is in this situation. Our chlorine is keeping this complex here that's ionically bonded very stable. Nothing interferes here at the top. It's just happy the way it is. And it's going to stay like this throughout this whole reaction, even at our final product. So we're going to have well, let's first go to the previous slide. I want to show you that we just used three hydronium ions back to back. One, two, three equivalents. All right. Now we are using two equivalents of water, and then back to back, two equivalents of hydronium ion again. So you kind of like it's not really like this, but you can kind of say that this water molecule that and these two water molecules are these two hydronium ions that just got their proton. So look at how this hydrogens just get shifted right back and forth, and it's just a very quick exchange. And every time it exchanges, it changes the formation of this group here. It takes away all the protons that's possibly attached to the amine here. First of all, that's the first thing that happens. It leaves it with no single proton. And then it skips the nitrogen and it makes the double bond that we so desperately need for this reaction to finalize, which then shifts the electron density down to the oxygen, which will shift towards a nucleophilic attack on the hydronium ion, which is extremely acidic. And because it's so acidic, it will all happen again after this primary alcohol was formed. And the reason why, it's not just because of the acidity of the hydronium ion, it also is because of the fact that water will become a leaving group when a triple bond forms between the diazonium group here, which is the two nitrogens. And that is why, yet again, we have a very thermodynamically favored byproduct that's going to participate as a hydronium ion as the reaction goes on. So now we go on here with the purple pink arrow. And our next slide, we come in here. This is the molecule we just created with the complex here. You see the complex? Remember, we have used a few hydronium ions, so we've got some chlorine anions that's available to stabilize the cation that now formed with a triple bond. And we want this to be as stable as possible because we don't want this nitrogen to be too much of an electron poor state that is going to interfere with our wish, which is going to be the attachment of the phenyl group at the terminal nitrogen, not the iso. So we essentially going to have chlorine keeping this site here just stable enough so that the electron density indeed does shoot up towards the cation, but not so much that the attack goes to the nitrogen. No, the attack goes to the terminal nitrogen, and it's a motion of electrons just moving like that, all towards the internal iso nitrogen. See it that way. And then our chlorine has served its purpose and it's just there on the sideline for now. We're going to get to that later when we talk about the acidic product. So, methyl orange, you can get two products. You can get either the neutral product with a pH 7, which is just basically the addition of dimethyl aniline. Only thing that's still needed for the neutral product to form at pH 7, your color of your flask of your substance is going to be your product is going to be orange, orange, beautiful orange. It's methyl orange after all. So let's just stop here for now and finish this before we move on to the second possible product that you can make. Now, the neutral product can also be two products itself, where you have normal temperatures that makes a trans product like this. And in heat, we have a minor extra isomer that does also show up, which is the cis isomer, where it's more sterically inert at the diazonium area there. So this methyl aniline shifts its electron density down to the ring, and it's from the ring that the attack happens to the diazonium group. This is our final attachment. This is our final step for the product. Okay, so we add dimethyl aniline, and it shifts electron density down, 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 and it jumps out, goes there, and goes towards this nitrogen, pulling it all up. So you also have to take note here that the dimethyl group there serves a purpose. It makes it's electron donating first of all, so it makes the nitrogen there very happy, stable, content. You also have the nitrogen not being it being sterically injured, so it's not going to be very nucleophilic, and it is now not very basic either. So yeah, it's just not basic, or it is not very nucleophilic either. But the aromatic ring does have some pi bond conjugation, and you can see it as like a stream that pulls. And it pulls the electrons from the nitrogen that participates in this pi conjugation. And it's in that moment when the electron density becomes a little bit too much for this little ring, and it shoots its electrons out towards the nitrogen there. All right. And we got our final product here. We don't have it. This is our final product. It's just that there needs to be some resonance included now. Take note that this is a cis product, but this is not the product, our final product, because look here, we still have aromaticity to be restored. We're still sitting with this very sterically injured proton that's so super acidic right there. And we're sitting chlorine. Chlorine went from here, from the internal uh, nitrogen there, the iso, and it went to the terminal dimethylamine at the bottom to keep that stable enough so that it doesn't protonate itself or get protonated or whatever. Um, so that's the role of chlorine there. And resonance do happen when water restores itself in the hydronium ion catalyst um, cycle. when it finally steals that last hydrogen, which is extremely acidic, like I said, it's sterically hindered. It is just so much squeezed in there. It's a tertiary proton with aromaticity to be repaired at just in a moment. So of course that's going to be removed immediately. This is the only hydrogen that I can see being removed more so than this one here because of the fact that this one can this is just more sterically hindered. It's just more forced. It's unstable there, right? Isn't it? I mean, there's a lot of things going on there. I'm sure that proton wants to make way for more bonds, you know? So, okay, this happens and the resonance shifts down, 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 all the way to the nitrogen, which will then send our chlorine goodbye to meet up again with the now formed hydronium ion that was formed here. And the water and the hydrochloride acid will restore itself. The cycle is complete. But um, look at the resonance distance. Okay, we're here at the middle of this molecule, and resonance only shifts down once after. Well, it's not even resonance; it's just electron density. So it's not really all that much resonance. It's electron density that shifts down. That's the correct term. But if we want to see this resonance, if we want to see it that way, for argument's sake, it's just one shift down. So it's just half the molecule. Now that makes the difference from the acidic product that you can form. So if you want a red substance, not an orange one, and you want your substance to be around pH 2, you add a very strong amount of hydrochloric acid, and you take just a little bit of the product, the crude product that you just made, that's orange, about 5 ml, and you add 1 drop of super strong hydrochloric acid, 12 molar, and then you get a red product. So let's have a look at this red product. This red product um, is now ready to have resonance. Well, again, this is not resonance. It's more of a electron density shift from the middle of the molecule all the way to the top, kind of top part of the molecule. And then the red, this is now pure resonance and pure resonance all the way down again. So it's got up and down. And you have to understand that in the color spectrum, of the visible spectrum, the extra conjugation and stability that the acidic molecule gives us is the reason why you go from a shorter wavelength, which is the orange color that you can observe with the eye, to a red color. So in fact, you see this protonation happen with the naked eye. You don't even need instruments. You don't even need a super duper microscope, which doesn't exist to see this. You can actually observe it with your eyes, how this protonation happens by the color shift. So we have little water. Water isn't even all that basic, but the hydronium ion here is extremely acidic. So we've got water at one end, and we've got a very strong acid on the other side, a very strong hydronium ion. And this hydronium ion here is going to be so acidic that it is going to pull all the electron density towards it so that that proton gets removed from it to form water. So that's the reason why neutral water can come in and deprotonate the ring there and shift the electron density via, some kind of resonance up, with it then shooting to this very acidic hydronium ion. Now we're sitting with a problem. We still have the cation here, and we still have aromaticity to be restored here. Now, why didn't the aromaticity win? Why did this thing shift upwards instead of just going downwards immediately? Because, I mean, there's a cation, there is aromaticity to be restored. So why? Why does it go up? Well, the reason is resonance, because this option here gives more resonance opportunity, and therefore it will go all the way up and all the way down. It's also because, in conjunction with the fact that we have this very strong hydronium ion here, it's also in conjunction with that. But ultimately, the reason is, and I mean, look here, these molecules are just already neutral, they're already in their favorite position. Why would they, I want to compromise it? But they do. They do because of extra resonance. It really wants to be the red color. And your professor is probably going to expect from you, this is the big secret of this whole mechanism, is which nitrogen on the methyl orange gets protonated in the end in acidic conditions. And the answer is it's one of the diazonium nitrogens, the one that's closest to the sulfonyl group there. So it's the one at the top. The reason being is it allows for the most resonance to continue. So we got it all the way up here and here, even in the hydronium ion, there's some shifting there, and then all the way down again. And we will now have the chlorine stabilizing that sodium there. And we've got protonated a nitrogen that's got an extra electron pair to make the pi bond back, to restore the pi bond so that the diazonium ion can be restored the way it likes it to be. And we restore aromaticity in the same way. So this chlorine that was now busy stabilizing the dimethyl aniline, it can now move up and stabilize there. And now I have to be honest, I'm not very sure if this proton here can be stolen back from the water that was formed here, then to make hydronium ion to give a hydrogen to the chlorine to restore back the cycle. That's just what makes sense, right? So I didn't draw it here. I'm not 100% sure about this, but I mean, it would be valid to argue that. I think there's some truth in that, but you will see here that that you can also just stop here. There's many videos, not just mine, that stops the reaction here. So, and the question really is which nitrogen gets protonated in the end? And the question, and this answers that question. So I think leaving your mechanism here makes that statement. But if you really want to, you can imagine this hydrogen joining that chlorine, um, restoring the neutral charge on this nitrogen. It's quite possible. It's quite possible. And I mean, we're talking about hydronium catalytic cycle after all. But this brings me to the end of this video. So you guys have studied out with me. Again, I'm going to tell you it's going to be a lot less confusing if you look at the bigger picture. And again, I'm going to zoom in and you can pause this video wherever you want to draw it like this. Oh gosh. Okay, this should do it, right? So yeah, do pause this video and be sure to see where the reaction comes from. Again, let me just get my pencil here on the side. Ah, there we go. So again, this is the first entry here. This is the first flask. We got a second flask coming in here. So this moves here and it splits in two. Here it stops. Stop, 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 stop. It splits here, but then it continues like this. And it joins this. Okay? That makes sense. Then it goes here, 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 here. And then it gets joined by this. And then you get your product there. Or it can go this way if it's not, maybe it is applied. So you see, there's your third entry. And of course, if you add hydrochloric acid, it does this. But it does this coming in from here as well, okay? So there should be an arrow too. So I hope that makes sense. Let me just take off all this pen marks here so that you can, zoom in on the actual molecules. This video is over. If you already have the molecules and you know, then you don't have to sit for this. This is just really zooming in to make sure that you know how the reaction works. And you can shift these molecules around to be aesthetically pleasing to the person who's going to write your report. But this is what I thought of. Also, this is not a minor product. This is a major product. Major. I'm very sorry that I wrote minor there. That's not the truth. Should be major. And shit, I hope I hope someone that watches this video watched it till here because that's the problem. This is the major. Here I wrote major. Major is when it is cis. Okay, so that's cool. That's the video, guys. Good luck. Have fun.